A very good morning to all of you. So I cordially welcome you all for this important course, that is applied thermodynamics. So in the today's classroom discussion topic is the very important one, that is a Rankine cycle. So the motivation to study this particular one is, so that is all the thermal power plants are basically works according to the Rankine cycle. So we have to know how to represent the Rankine cycle on PV diagram as well as on the TS diagram, and what are the working principles of the Rankine cycle. So at the end of this particular lecture, I'm expecting the outcome is you have to represent the Rankine cycle properly on PV diagram as well as on TS diagram. So here, the basically first of all you have to plot. That is, how can you represent this particular the Rankine cycle? So in the previous session, I told you that there are four important components are there in a thermal power plant. The first one will be the boiler, second will be the turbine, condenser, as well as the pump. So you have to arrange them in a proper sequential manner. So boiler, that is the heat is basically given to the boiler, that is by burning the coal, by combustion of the coal. So here the steam is basically leaving, that is the exit of the boiler is represented by 1. The steam is going to the steam turbine. So here we are able to produce some amount of the mechanical power, that is the WT, work done by the turbine. So turbine exit is given as the 2, that is the exhaust steam is leaving from the turbine. Now it is going to the condenser. So condenser is a heat rejection device, that is a Q out. So now here the condensed steam is basically going to the pump. So the pump is a device which is basically used to increase the pressure of the working fluid from the condenser pressure to the boiler pressure. So there will be some amount of the work is basically required to drive this particular the pump. So that is the some amount of the work input to drive the pump is basically taken from the turbine work. So that is, this is basically a shaft. That is, some amount of the work is basically utilized to drive this particular the pump. So now this is going to the boiler. So 1, 2, 3, 4 we have represented here. Now how can we represent the same thing on the PV diagram? So it basically depends upon the quality of the steam. That is the point number 1. So if the point number 1 is wet, then the PV diagram representation is different. If it is dry, then it is different. If it is superheated, then it will be different. Now in this particular PV diagram, now you can see for dry steam, that is for the dry steam, first one is the dry steam. That is dry steam is basically represented by 1, 2, 3, 4. So just you see here is a point number 1. So if this particular point number 1 is a dry saturated steam is leaving the boiler, so then the point number 1 is to be located on the saturation line corresponding to, so it is corresponding to is the boiler pressure. It is corresponding to the boiler pressure. So boiler pressure, locate the point number 1. Next 1, 2, 2. So that is a turbine. Always in the turbine we are able to have the constant entropy expansion process will be taking place. That is represented by drawing a curved line is a 1, 2, 2. So this is isentropic expansion process. Next to 2 to 3, always condenser is a heat exchanger in which we are able to have the constant pressure heat rejection only. So it is a 2 to 3. And whenever 3, it is always we are assuming that it is a saturated liquid is leaving the condenser. So that is, this is basically the condenser pressure. So draw a condenser pressure line wherever it is meeting the saturated liquid line, that is your point number 3. And next 3 to 4. 3 to 4, once again it is isentropic compression process in the pump. So 3 to 4 is isentropic compression process. So draw a curved line. So wherever this curved line is intersecting this particular one, so this is the point number 4 and this is my point number 1. So this is my point number 2, is point number 3. If the steam is leaving the boiler is superheated steam, if it is the superheated steam, then it is modified as 1 dash, 2 dash, 3 and 4. Now you can see 1 dash. Now it is in the superheated state. So 1 dash to 2 dash. Now it is by 2 dash. Now 2 dash to 3 and 3 to 4. So this is a representation of the Rankine cycle of the dry steam as well as the superheated steam. So if it is the wet steam, then the point will be taken here, 1 double dash. Now it will be drawn like this. So it is can be represented as 1 double dash, 2 double dash, 3 and 4 if it is the wet steam. So that's why to draw the Rankine cycle, first of all, you should know what type of the steam is basically leaving the boiler. So based on that only, we are able to get whether it is the point number 1 or 1 dash or 1 double dash. That is important one. So the same thing you are able to represent it on the TS diagram. Now it is on the HS diagram. That is very, very important one. So 1, 2, 2, I already told you that is the isentropic expansion process which is taking place in the turbine. 2 to 3 is a constant pressure heat rejection process which is taking place in the condenser. 3 to 4 isentropic compression process which is taking place in the pump. And 4 to 1 it is a constant pressure heat addition process which is taking place in the boiler. So now you can see it's the point number 1 which is taken on the dry saturation line. So this is my saturation line. So 1, 2, 2. So similarly 1, 2, 3, 4 is representing it is a dry saturated steam. And if the boiler exit is the superheated condition, so now it is a boiler pressure. So on this particular boiler pressure, locate it as 1 dash. So 1 dash 2, it is a 2 dash. Next is the 3 and 4. So 1 dash, 2 dash, 3 and 4, it is representing now superheated steam. The same thing is represented here. What is the 1 to 2, 2 to 3, 3 to 4, as well as the 4 to 1. And how can you analyze the Rankine cycle? So that is just you go through the steady flow energy equation. So from this particular steady flow energy equation, we are able to know that delta H is equivalent to is a Q minus delta W, because all of you know the steady flow energy equation. So from this particular one, so this is very, very important formula, that is how can we find out the pump work? The pump work is always equivalent to V into P1 minus P2, that is minus V into dP. So minus V into dP, that is the steady flow energy equation. How can you find out the work? So V into P1 minus P2, that is a formula which is used to find out the how much amount of the work is needed to drive the pump. And here you can see the turbine work is equivalent to H1 minus H2, and how much amount of the heat is supplied to the boiler, it is H1 minus H4, and how much amount of the heat is rejected from the condenser, H2 minus H3. So finally, our aim is to find out the efficiency, that is the net work done divided by heat supplied. And you know that the net work done is equivalent to turbine work minus pump work, because some amount of the turbine work is basically used to drive the pump. So W2 minus WP. So WP, just now I told you that it is a V into delta P. So V into P1 minus P2. So W net also can be found out as is a Q in minus Q out. So this is the formula of W net. And the Rankine cycle efficiency is equivalent to is the net work done is also equivalent to heat supplied minus heat rejected, that is the Q in minus Q out, is the 1 minus Q out by Q in. So the formula is 1 minus H2 minus H3 by H1 minus H4. So it is the another important point here I have written. In order to avoid erosion and corrosion, of the turbine blades, wet steam is never allowed to enter into the turbine. That is the exit of the boiler, preferably always it is the dry saturated steam, or it is the superheated, steam only is basically allowed. Superheated steam is only allowed. That is, if the wet steam is basically leaving the boiler, then it is basically posing all these particular problems of erosion and corrosion. So this is the representation of the Rankine cycle using the wet steam. So I've already told you that the wet steam means it will be it is having some dryness fraction value. So here you are able to find out what is the dryness fraction value at the point number 1. And similarly, another performance parameter is known as the relative efficiency, which is also known as the efficiency ratio, which is defined as actual thermal efficiency to the Rankine efficiency. So based on this particular input, let us try to answer few important questions which were asked in the previous GATE examination. So consider the following processes: constant pressure heat addition, adiabatic compression, adiabatic expansion, constant pressure heat rejection. The correct sequence of these processes in the Rankine cycle is, that is, always you have to remember the components arrangement, sequential arrangement in a thermal power plant. So always you have to remember one important one, that is the boiler, followed by turbine, followed by condenser, followed by pump. So that is always you have to remember BTCP. There is a boiler, turbine, condenser and pump. So in the boiler always is a constant pressure heat addition will takes place. Turbine always is a adiabatic expansion will takes place, that is followed by 1, 3. Condenser always it is a constant pressure heat rejection process will takes place, 1, 3, 4. And pump always it is a reversible adiabatic compression process will takes place, that is a 1, 3, 4, 2. 1, 3, 4, 2. So this is the basic processes which are taking place in the Rankine cycle. So now the answer will be 1342, but the options are not there 1342. So here no option is there in the terms of the 1342. Now the same thing can be written as, because it is a cyclic process, it can be written as 2134, or it can be written as 4213, or it can be written as 3421. So that is either this is also right, this is also right, this is also right, this is also right. So now go through the options, whether which answer is there in the ABCD. So now the 2134 is there, that is this is also right. So 2134, so the answer will be C. Next one. In a Rankine cycle with the maximum steam temperature being fixed from the metallurgical consideration as the boiler pressure increases. Because why we are fixing the metallurgical consideration point of view, we are fixing the fixed temperature. Because with increase in pressure, the state of steam shifts towards left, and thus on the expansion quality of the steam will be decreases. So that's why the answer is B, that is the quality of the turbine exhaust always will decreases. What is the reason? Because maximum steam temperature being fixed from the metallurgical consideration, as the boiler pressure increases, the quality of the turbine exhaust always will be decreases. So similarly, which one of the following statements is correct? So go through all these particular the ABCD options. Then the right answer is the B, that is the efficiency of the Carnot cycle is always high, but the work ratio is low in comparison to the Rankine cycle. That is why the Rankine cycle is preferred over the Carnot cycle. For this particular question is given in the ES 2007. So such type of the questions will be asked in the various competitive examinations. So you should be in a position to answer the important questions on this particular the Rankine cycle. So thank you one and all for listening this important lecture on the Rankine cycle.